All right. So here's chapter 11. Not sure. Second lecture. So now we're still doing rectilinear motion, but we're going to talk about relative motion too. And so the in the first lecture we did section 11.1. We did a few problems. I will, as I said, is that there's obviously more problems that we could do than we have time for in the 50 minutes. So I will be posting additional problems that I do like this. I'll record and then I'll put them up there, and I'll do that even after we're live, just because we still only have 50 minutes to cover the class. So you guys can see my screen right now, assuming if something goes awry and I'm talking and you're not seeing what it, please someone speak up. So I'm assuming you can see my Canvas or PowerPoint right now. So today we want to look at equations from 11.1, the ones that we've already looked at, but continue with that. And to those, we're going to add constant acceleration. The constant acceleration equations you guys have seen in the past, I know from physics, an example, x equals x naught plus vt plus 1/2 at squared. And we'll do a problem like that. And then we'll talk about relative motion. And relative motion, we're going to see over and over again. And so it's similar to the relative motion that you looked at in physics, where it depends on your reference frame, will determine what you see. But the first problems we'll do are fairly easy. They're just vector addition, and they're straightforward. And so again, we're sticking to 2D for the moment. All right. So first, what does a live transcription mean? Can you explain that to me? Sure, why not? Anyway, sorry, there's someone asked me a question. So the conceptual example that I have here is a ball's thrown straight up in the air, and it reaches with initial speed of v naught, it reaches a maximum. And so when it hits the maximum point, h, just before it starts to fall down, another one is launched. And so the question is, where will the two meet, or where will they cross? So we don't know what we don't have any numbers, but we can surmise a few things. One is y equals the maximum height, or in the first answer. These are the different answers we have. So obviously they're not going to cross at maximum height, because when it reaches maximum height, there's no way the other ball can get there instantaneously. And they're both not going to meet when they hit 0. That's not going to work. And so they got to meet somewhere either halfway, above halfway, below halfway. So I would say that what's reasonable? Well, when you think about a ball, when it first takes off from the ground, or anything with initial velocity, it moves the fastest the first half of it takes less time to go the first half its distance than it does the second half. So the time it'll take the ball to fall from its height compared to the time it'll take the second ball to reach the half the height is going to be less, right? So the second ball is going to get to the half the height quicker. Therefore, we're going to meet somewhere above h/2. So I probably could have said that in fewer words, but I think that does that make sense to everybody? So the ball is going to fall slow, whereas the other ball is going to go fast, and they're going to meet somewhere past halfway over 2. All right. Okay, so another example. So this one, and this one I picked because it's not difficult dynamics wise. It has a couple of it has an integration and a derivative in it. And that's what I've noticed about these earlier problems, is a lot of them are more calculus intense and algebra intense than actually the dynamics. So it's not really the dynamics that can hang you up, it's how familiar you are with your calculus. So you guys are probably at a better advantage than me, because my calculus is okay, but it's not as fresh as your guys' is. So, okay. let's look at this problem here. Now, you notice I did post the examples on a separate sheet on Canvas. So if you didn't see that, I will do that for each lecture. I'll post the actual PowerPoint, but I'll also post the examples so that you can have those separately, because I'm going to toggle between this and the document camera, mainly so that I can see when I record, it'll show up on the screen. That's the main reason. All right, so let me stop. What's going on here? Bear with me. Sorry, I don't know why this thing's not letting me. Ah, there we go. Okay, so you should be able to see my screen now. Hopefully it's, yeah, it should be in good focus. Sorry, I'm just having a few technical issues right now. There we go. All right, so we have the ball. Here's the ball, it drops. And it drops down. And so it's dropped, it hits the water. And we're told that when it hits the water, it has a V initial of 16.5 feet per second. All right. And after it hits the water, it has an acceleration of 10 minus 0.8 times velocity. And then we're told that it takes 3 seconds to hit bottom. Okay, so this is all our given right here. V initial, that, and that. All right, so we want to find A, the depth of lake, and B, the speed on impact. So how fast is that ball going when it hits? All right. Okay, so if we, knowing that, we can pull up one of our equations, A equals dV dt. All right. And so if we rearrange that, we know that dV over A equals dt. And so we can then substitute in this down here. And what that gives us is the integral of V naught to V dV over 10 minus 0.8 V equals the integral of 0 to t dt. Okay. So we'll do a U substitution for this. And so on this one, I'll go ahead and walk you through it. U equals 10 minus 0.8 dV. And du equals negative 0.8. I'm sorry. Yeah, du equals 0.8 dV. All right. So we know that negative 1 over 0.8 times du equals dV. And
Wouldn't
so,
the first part just be U equals 10 minus 0.8 V, not dV?
yes, I'm sorry about that. Yeah, got ahead of myself. Thank you. Like I said, my calculus is rustier than yours. So once we get that, then we can go ahead and we know that we just integrate 1 over u, which is essentially the log of u. All right. So if we go ahead, then what we end up with is, therefore we end up with is a negative 1 over 0.8 natural log of 10 minus 0.8 v. All right, evaluated from v naught to v, and that's going to be equal to t. Okay, so now really we have this equation like this, and really what we want to do now is we want to get it in terms of v. We want to get t in terms of v. So we want to turn this into v equals something. All right, so I won't skip this. I don't want to just skip the simplification. So I'm gonna go to another sheet of paper and let's go through that. And what we have then is negative 0.8 t equals natural log of 10 minus 0.8 v over 10 minus 0.8 v naught. All right, so just evaluating it from v naught to v. And so, and then rearranging. And so then we move the 0.8 to the other side, and, or actually, no, we don't do that yet. We just raise it. So we're going to take the e to each side exponential. So we get e to the negative 0.8 t, and that's going to equal just 10 minus 0.8 v over 10 minus 0.8 v naught. All right. So that then becomes 10 minus 0.8 v naught e to the 0.8 t, negative t, and that equals 10 minus 0.8 v. All right. So then we arrange it a little bit more, rearrange it a little bit more, and we end up with 0.8 v equals 10 minus 10 minus 0.8 v naught e to the negative 0.8 t. Okay. So we divide both sides by 0.8, and that gives us v equals 12.5 minus 12.5 minus v naught e to the negative 0.8 t. And finally, we get our terms of v. V equals 12.5 plus 4 e to the negative 0.8 t. And that's with substituting in v naught equals 16.5 feet per second. Okay. So we put that in here, and this is what we end up with, 12.5. All right, so that's that. So now we have v in terms of that. And so we're not done though, because really what we're looking at is we're looking at the distance. So with that, what we want to do is we know that v equals dx dt. And so we can rewrite this as v dt equals dx. And so what we end up with then is integral from 0 to t.
Can you scoot your paper down?
Yes, thank you. We end up with 0 to t. Get my microphone, or sorry, my camera up here a little farther. There you go. 12.5 plus 4 e to the negative 0.8 t, all dt, and that equals just the integral of 0 to x dx. So we can, again, we do a U substitution. I know you guys can do that. But if we, again, we have U is just going to be equal to negative 0.8 t, and then du is going to be negative 0.8 dt. So if we plug that in, we end up with this being 12.5 t minus 5e to the negative 0.8 t, evaluated from 0 to t, and that equals just x. Okay, so we need our constant of integration. So we're going to evaluate this from 0 to t. And so if we do that, if we put in 0 into here, we get a 5. If we put in just t, obviously that's what the equation is. So we end up with the final, when we evaluate it, we get x equals 12.5 t minus 5e to the negative 0.8 t plus 5. So that's our equation of position. So all that to get these two equations, right? So far we really haven't done any dynamics. All we've done is some calculus. And so here we have these, and the actual calculation to get the answers then is, sorry, move around, leave that like that. So we know that at t equals 3 seconds, we know it hits the bottom. So now we can just find the position. So x equals 12.5 times 3 minus 5e to the negative 0.e times 3 plus 5. And so if we plug that all in, we end up with 42.0 feet. All right. And then for velocity, we want to know what is the velocity at the time of impact. Well, we know the time of impact is 3 seconds, right? It takes 3 seconds to get there. So we can pull in this equation here. So I'm going to rewrite that. V equals 12.5 plus 4e to the negative 0.8 t. And so I plug in 3 for t, and I get V equals 12.86 feet per second. All right. So a little tedious, but we got through it. So I would say that, again, most of the problems vary in complexity based on the calculus and algebra, but not so much on the dynamics as far as what I've seen so far. So now this, to give you an idea, this would not be a good exam question because I don't want you to sit there and, I mean, all of the calculus isn't difficult. It's not what I want to test you on, especially if I'm giving you 2 or 3 questions. I don't want you spending all your time doing the calculus. I want you to understand the concept. So I'm not exactly sure how I'm going to set the midterms. They might have some conceptual parts and some calculation parts. I really have to think about how I want to do it to best show or the best way for you to demonstrate your knowledge to me. All right. Now going back to uniform accelerated rectilinear motion. So this is after 11.1 and 11.2, we, again, since we're starting out at a pretty basic level, we're just going to take our relationships dv dt and relate that to a as a constant. Okay, so we have our constant acceleration equations from physics. we have our relationships, especially the one dv dx times velocity equals acceleration. So you'll be using those, and I would, write them down, have them in your notes. But that's the first thing I would look at when you're looking at the problems, to see how you can arrange your integration or your derivatives so that you can take advantage of these equations. Now, the next topic is relative motion. Now we'll do some examples of relative motion, but you probably remember this from physics too. I should say physics also. When you have relative motion, it depends on your reference frame. In the first examples we're going to do are fairly simple. We can use vectors to add them as they get a little more complicated. But if we're looking at something in a straight line, because we're still in rectilinear motion, then we know that xb relative to a is just equal to xb minus xa, and we can see that on the line that drawing there. And a good way to remember this is that if you write the equation, whatever the letter is first, that's the first letter on the right side, right? So you write xb relative to a is equal to xb minus a. And then typically we'll rearrange the equation and we'll have xb equals xa plus xb relative to a. And so whatever the first letter is, that's the one that goes on the left side of the equation. So that leads us to the idea of relative motion, and the simple examples just using a pulley. And what we can see, for that example, it's like it's hiding from me. I apologize when my pieces of paper disappeared. Okay, well, we can look at this one here, and let me explain how this works. And when I do an example, it'll make more sense. But here it is. I apologize. So I'm going to explain it, then I'll show it to you. So here we have, in this cable here, we have one cable that goes throughout the whole system. And so we say it's 1 degree of freedom. And the reason being is that if A moves, B has to move. You can't move A independent of B, since they're all connected by 1. And so when we do a problem like this, first thing we do is identify how many degrees of freedom. So in this case, we have 1. And then we pick what's called the datum. And all the datum is a fixed reference point where nothing moves. And it could be a line through CD. It could be a line through the 2 eyelets at the top. It doesn't matter, as long as it's something that's not moving. And then what we do is we draw a line down to each object. And you could go to the top of A, the bottom of A. It really doesn't matter because we don't have any physical distances. But what we're doing is we're relating the motion of A to B based on how the pulley is configured. So if you look at the length of the ropes, the whole rope itself is constant, right? No matter what A and B do, the rope doesn't change length. And so from that, we can develop equations. Now, what are those equations? Well, if we look at XA, we know that XA is going to go up and down, but as XA goes up and down, that's XB is going to go twice that, or 2 times. So what our equation looks like is, for something like this, is we have XA equal or plus, 2XB is going to be a constant. Now, the reason we say it's a constant is because this rope that goes around the pulley here and here, that's a constant. It's always going to be there. But as A goes up and down, it's going to go just 1. It's moving as 1, whereas you have 2 ropes moving here for B. That's where the 2 comes from. So if we take the time derivative of this, we just get velocity of A plus the velocity of B, or 2 times velocity of B, equals 0. And same with the acceleration of A plus the 2 times acceleration of B also equals 0. Okay. Now, if we look at the next one.
Why did you do equals 0?
Because when I take the derivative of a constant, it's a 0.
Thank you.
Yeah. So if I go back to this, sorry. We go look at the second one. So here's a different one. And in this one, we have 2 degrees of freedom. And the way we know that is if we look at the different pulleys, we see that if we were to hold A constant, B and C can move independent. So A doesn't have to move for B and C to move. B can move, doesn't have to move for C and A to move, but at least 2 of them have to move. So there's only 2 degrees of freedom. And again, the same thing, you're going to pick your datum, you know the length of the rope remains constant, and then you're going to develop your equations. So if we look at that the same way, and we have an image like this, then we look at XA over here, we see that there's 1, 2 ropes. See, unlike up here, XA just had a single rope to it. Here, it's determined by both of these. So we're going to write that as 2XA. And then when we look at XB, we see that XB has 1, 2 ropes also that determine its motion. So plus 2XB. And then, but XC just has a single rope. So that's going to be XC. And that equals, sorry, a constant. All right. And the same thing, if we do the time derivative, we get 2VA plus 2VB plus VC equals 0, and 2AA plus 2AB plus AC equals 0. All right. So that's how those work. And so it makes sense that if we're given certain relationships, say, for example, if we're given the velocity of A, then we can do some rearrangements and substitution, and we can actually find the relative velocities of all of the different ones. And so these end up being just a lot of substitution, but and that's why I put a couple on your homework, because if after you do a couple, I think you'll have a pretty good understanding of it. So what I want to do now is I want to do an example. So if we go back to
Real quick, Professor.
Oh, sure.
On our homework, I think some of the answers are cut off. Just wanted to give you a little warning. I'm pretty sure. I don't know if anybody else can back me up on that.
They're cut off.
Like
Really?
it just won't show the answer, or like it says answer and then there's nothing after it.
Oh, interesting. Because what I did is I want to give you the answer. I'll check that. Thank you for bringing that up. As soon as I'm done with class here, I'll check that up and fix it. So if we look at the next example, or this is the actual example we have, here we have an elevator, and this is a good example of an elevator. When you think of how a real elevator works, you have a huge counterweight, you have the elevator itself, and then you have a motor. And so by having this huge counterweight, the motor doesn't have to really work that hard, because all you're doing is you're just moving this balance off. So clever idea. Anyway, though, we're given that it has a constant velocity of 4 meters per second. And we want to determine VC, VW, VC relative to E, and VW relative to E. And so remember, our generic equation for relative motion is, if we don't have an A here, but it's generically C relative to A is always C minus A. So you just take the first letter minus the second letter to get your equation. So let's go ahead and look at that. So here you have, again, your diagram. So if you don't have that written down, or if you don't have the image in front of you, take a second to sketch it out. And so we have our motor here, point C. So we have a line YC comes down to here. And so we're defining this direction as positive. So we're saying that as you go this way, it's positive. So obviously if you go up, it's negative. And so we're saying YW and YE. Now the script doesn't matter whether we call it YS or X, whatever, it's irrelevant. But the main thing is that you identify some datum, which I've identified as the very top, and then you identify some point on your object, and then you draw a line to it so that you can then relate the motion to each other. So if we do that, what we get is for cable A, we have YC plus 2YE equals a constant. All right, so if we're not sure, we see that YC, see how it moves up and down, but E, on the other hand, has 1, 2 cables. So each of those have to move for every inch this moves, these have to move half that, right? So, or not twice that, but so they move twice. So we get this relationship here. And then we know that if we take the time derivative, we get VC plus 2VE equals 0. But remember from the problem, if we look at the writing of the problem, we're given that VE is positive 4 meters per second. So therefore, we can write VC is equal to negative 2 VE. And so VC is equal to, doing the complex math, we get minus 8 meters per second. So I'm putting in 4 for VE. And so since it's negative, it means it's going up, or 8 meters per second up, because we defined down as positive. Okay. So then the second one, so this was the finding the velocity of C. And then in B, we wanted to find velocity of W. And so for W, if we go back to our picture, we see that YW and YE both move as a factor of 1. So YW and YE are both 1. So when we write our equation, we just have YW plus YE equals a constant. Therefore, VW plus VE equals 0. And so in this case, VW equals negative VE. And since we know that VE started as 4 meters per second, and again, that was down because that was positive, then VW is going to be 4 meters per second going up, since it ends up negative.
Good question.
Yes.
Do we write as two? So is there a separate equation for every time there's a different rope, basically?
Yes, that's correct. If you have more than one rope, then you have to have a separate equation. That's correct. Okay, so that's A and B. And then remember that for C, we wanted to find, we wanted to find VC relative to E, right? That's what we're trying to find. We know that though just equals the velocity of C minus the velocity of E, right? So C minus E. So that's the easy way to remember. C minus E, C minus E. That's how it is. So in that case, we know VC was negative 8 because it was going up, minus VE, which is negative 4, it's going up. So we get a total of negative 12.00. So going, or 12.00 going up. So you can write your answer either way, negative or with an arrow. It's kind of just like in statics when we're doing reactions, depending on which direction they're pointing at. So meters per second up. We don't need the up if we have a negative though. And of course, we want to put the units meters per second. And then we have VW relative to E. And that, of course, is going to be VW minus VE. And so similar, in this case, we have minus 4 meters per second minus 4 meters per second gives us negative 8 meters per second, or 8 meters per second going up. Okay. So this is, I think these problems are nice because they're fairly simple. And as we get more into more complicated problems with relative motion, you'll have this foundation in which to build upon. Okay. Any questions? Okay. All right. So I had a question. Can you explain the factor of 1 for VE in part B? Did that question get answered? I don't always look at the chats while I'm going, so so I'm just looking at it now. It says one asks, do we have to remember complex integration techniques for test problems? No. I think U sub is reasonable, but I don't think, I'm not going to have partial fractions or some of the other gnarly stuff you learned in 142 if you took calculus here. So anyway, I hope that answered your question. But all right, let's go ahead and go back to this. Let's do another example. All right, so here we have an example I've drawn out. You have a motor and it draws the cable in at a rate of 100 millimeters per second. And so if you think about your motor, when we say drawing it in, so we want to, first we want to draw what that looks like. So I'll show you that in a second. And then this is what the criteria says. So we want to determine the velocity of A and the velocity of B. So we notice right off the bat that we have two different cables here. We have A that connects to B. And you should be able to see that for A, it's going to be 2A. So 2YA plus Y of B is going to be equal to a constant. And then for this, you're going to have 2Y of B plus the motor is going to be your constant. All right. So then we know the motor starts at rest. So we're going to try to find the accelerations, and then we're also going to find the velocities. So let's go ahead and walk through this one. And here we have our picture. So let me point out things. So here I've called it S. So distance A goes to A, could have been Y, doesn't matter, so that's not important. S is very common for distance though in physics. So, but here we have this distance A. We know it's 2 of these to 1 of those. And then for here, we know it's 2 of these to this point on the motor, because the motor's going to move once, these are going to move twice. All right. So knowing that, we know that that 2SA plus SB equals a constant, and 2SB plus SM is equal to a constant. So take the time derivatives, we get 2VA plus VB equals 0. 2 acceleration of A plus acceleration of B equals 0. 2 velocity of B plus the velocity of M equals 0. And 2 the acceleration of B plus the acceleration of M equals 0. So we have those. And so we're told that the cable draws in, so 100 millimeters per second, that point is drawn in. So we're going to say that drawing in is the positive direction when the cable is drawn in. And so we're asked to find, first off, find VA and VB. So we want to find the velocity of A and velocity of B. So, well, we're going to have to start with this equation here, right? Because we know that's 100 millimeters per second. So we know that VM is equal to, or I should say half VM is equal to negative half VM equals the VB, right? So if we know that, then essentially we have a positive 100. So negative a half of 100 gives us negative 50. So that means that VB, if we define down as positive, VB is going up, all right, at a rate of 25 millimeters per second. And so I think mechanically, that's probably easy to see. If this is coming in at 50, then this is being halved because you have to move the rope twice as far. So it's going to go, you're basically pulling up on this side and that side. So you have half the speed in order to be constant. So this is 50. This is going to go up at 25. All right. And then we're going to do the same thing to find our other value. And so we want to find, we're asked to find VA and VB. And so we know that VA here is essentially half of VB, right? So if we write that, we get VB equals 1/2, or I'm sorry, VA, apologize, equals negative 1/2 of VB. And that's just going from this equation here. So we've already established that's this. And so then we know that this is going to just be half of that then. And so we end up with VA equals a negative half oh wait, no, I apologize. This was 100 up here. So this I put in, yeah, so this is 50. Oh yeah, this is 50, but I should have put the 100 here as 50. I wrote 25. I'm sorry about that. I was getting ahead of myself. This is 20, this is 25 here. You guys got to call me out on these. So you got 1/2 of VM plus VB. We know that VB or VM is 100. So therefore half of that is going to be negative 50. So then if we plug it in here, then VA equals negative 1/2 of negative 25.
That 25 is supposed to be 50 still. You crossed out 25 and then wrote 25 again.
Oh, yeah, sorry about that. Yeah. So then that's 50. This is half. So yeah, so VA ends up being then 25 millimeters per second, and it's going down. There we go. Now we're correct. So VA is going down positive, VB is going up at 50. All right. Sorry about that little snafu. Okay, so then the second part asks us to find, it says the motor starts from rest and releases cable at A at a constant rate of 5 millimeters per second squared. So when it says it releases, that means that our acceleration here is already negative, right? Because it's releasing, it's going that way. We're defining this as positive. So we know then that the acceleration at M is equal to negative 5 millimeters per second squared. All right. So if we follow, it's just the same idea as before. We know that 2 times the acceleration of A plus AB equals 0, and 2 times the acceleration of B plus acceleration of M equals 0. And so we get the same relationships as before. We have AB equals -1/2 of AM. Therefore, AB equals a positive 2.5 millimeters per second squared. So if we plug that into there, then it just is positive. And then if we go over here, we do the same thing. We say A, acceleration of A is equal to -1/2 of acceleration of B. And so the acceleration of A is equal to -1/2 of 2.5 millimeters per second squared. And so therefore we get -1.250 millimeters per second squared for the acceleration of A. Okay. And then the last thing it says is, what is the velocity of A and B at 3 seconds? So now we started at rest. So we're saying at time equals 3 seconds. Now we know the initial velocity of A equals initial velocity of B, which is 0. All right. So then we just go back to our old kinematic equation. V of B is equal to VB naught plus the acceleration of B times time. And so we know the acceleration of B is 2.5. So we know it's going to just be 0 plus 2.5 times 3. And we get velocity of B is 7.5. And it's positive, so it's going down because that's our direction of positive. All right. And then the same thing, we know that VA is equal to VA naught plus AT, a acceleration of A. And so in that case, we have 0 minus 1.25 because acceleration of A is negative, and that's times 3. And so our velocity of A is going to be -3.75 millimeters per second, or 3.75 millimeters per second going up. Okay. All right, so we're about out of time, but one last thing I wanted to mention was, if I'd had time, I would have gone over this problem, but since I can't, I'm going to go ahead and do that and post it on Canvas. So I'll just write out the solution, kind of like I do here, narrate it, and then I'll post it. And it's up to you whether if you need the extra help, the extra problems will help, then that's just something I'm offering. But obviously I don't have time to do this, and I will do that throughout the whole quarter, even after we're live, because we only have 50 minutes for lecture. And one last thing is, this problem here is related to doing things graphically. So if you recall, doing things graphically, it has to do with using the idea of the area under the curves of the position, velocity, and acceleration in order to find different values for velocity and acceleration. So just another method of solving. Okay, that's all I have. If you have questions, I'll be in office tomorrow from 11 to 1. Otherwise, I'll see you guys on Friday. Thank you.
Thank you, Professor.
Thank you.
You're welcome.
Thank
Thank
you.
you.
Thank you.
Have a good day.